KBF24-1. Knots and braids. Fall 24. And this is part 1. And this series should be out of... Aw, you're pretty sad. Should be out of 4. So, part 1 out of 4, knots and braids. What are we talking about today? Why knots? Why are we talking about knots and braids at all? This is supposed to be some sort of technology thing. What do knots and braids have to do with technology? So, why knots? Early interest in knots dates to the late 19th century. Dates to the late 19th century. Concept of ether. Concept of ether. If you're not familiar with this, it's understandable. It has kind of disappeared. The concept of ether was basically that there had to be some sort of medium through which light was traveling. So light is some sort of wave. Waves travel through some sort of medium, such as the waves that you think of on water, traveling through water. So what medium does light travel through, since we know that light is a wave? Of course, they were right in the 19th century about light being a wave, but it turns out that there's a rather weird solution to this. Light is both a wave and a particle, which means that we don't require the concept of aether. But at this point, they didn't know that, so they did need something like aether in order to explain how light moved from distant stars to the Earth, which was obviously happening because, we were looking at them. Yeah, good stuff. So, the aether was basically a medium through which light could travel. Through which light could travel. In this era, therefore, most scientists didn't believe in true vacuum. And funnily enough, one of the reasons I bring this up is this idea has kind of resurfaced. In the 19th century, we're not going to believe in true vacuum because we need some sort of aether permeating space. But in the early 20th century, this idea in quantum mechanics is going to emerge essentially of particles spontaneously being created and sort of disappearing inside of every fabric of space simultaneously all at the same time. It's just sort of a natural thing that has to occur. This is kind of cool. There's a lot of predicates in these ideas for later influential ideas in math and physics. So, in this era, most scientists didn't believe in true vacuum. Lord Kelvin is the guy who really is going to kick off our study of knots, and whose name is quite famous. If you haven't heard of Kelvin yet, you will in the future. 1824 to 1907. We're just on the edge of the quantum revolution there, poor guy. Hypothesized that atoms... I'm spelling that correctly. Yeah, close enough. Hypothesized that atoms were just knots in aether. So this is actually quite a common scientific technique. He's taking two essentially unknown scientific principles and he's using them to explain each other at the time. And while that doesn't really make masses of sense right now, it is quite a sensible technique on basic ways, right? It's something we don't understand. If we can kind of group these things together and carry out experiments to test them both at the same time, we can save a lot of effort and energy, even if our hypothesis doesn't end up being true. So it's very practical, even if it doesn't work out a lot of the time. So, while this idea is later disproven, as we've already talked about, It had two major impacts. First, in mathematics, or math, or maths, depending on where you're from, it started the enumeration of knots. And Kelvin himself starts keeping track of how many knots there are and numbering them, essentially. It started the enumeration of knots and knot theory, which is the name for sort of the associated field of mathematical research. And two, in physics, how do I phrase this? This concept was later adopted. That's good. By string theorists. To explain how strings form fundamental particles. Basically, the strings can tie themselves into, it's kind of a pleasing idea. They tie themselves into different knots, and then that shape represents an electron or something. String theory is, of course, it lost a lot of favor recently. You can go do plenty of research, find out why that is. Ultimately, any of the sort of testable predictions of string theory have not turned up, and theoretical physics as a whole is kind of in this searching period where there's a couple challenging results that have been kicked up, but there's nothing that's like really, there's no like crazy groundbreaking piece of research that's forcing us in some brand new direction, and there's also really no great theoretical advance that people are trying to plumb the depths of. It's kind of a weird moment, so hopefully that's changed in a couple of years and I get to be more excited about theoretical physics. Anyway, moving on. Intro to knots. So we're going to concern ourselves on a basic level with the sort of enumeration of knots. How is it possible that you can like enumerate knots, that you can number them, that you can keep track of how many there are in that sort of way? In order to do that, though, we first have to define what knots actually are. So we can think of knots like this. If we connect both ends of a string together, can the knot ever be untangled? Can the knot ever be untangled? This is untangled. This is to avoid, clever people being like, well, we could just cut through the knot with some sort of sword or something, and then boom, we would have solved the problem, easy peasy. This is not valid for this. The assumption here is that we have some sort of crazy knotted thing, and that it loops totally back together, and then we can perform all sorts of manipulations on the actual knot itself, and hopefully it becomes undone. What's cool here is it might not be apparent to you that this is even possible to order into some sort of untieable or tieable state. And the idea that there's in fact different untieable knots under this condition that you can then enumerate is kind of a cool idea, right? That's where we're sort of starting from. So the simplest knot that can't be untangled is called the trefoil. Well, actually, it's not quite true. It's really the unknot. But the unknot is kind of a disappointing knot, at least conceptually speaking. The trefoil is the simplest untieable knot that actually has crossings. And I should be so good at drawing this thing. There we go. That's pretty good. This is the trefoil. This is the 3' knot. It's got 3 crossings, and it's prime. Yeah, good stuff. These are pretty cool knots. You should try and make them yourselves with a piece of string. Ironically, you have to knot the string in order to make the knot. But yeah, it can be pretty fun. For very simple knots like these, the variations are typically quite easy to spot. Easy to spot. Our unknot, for example, one of the simplest. This, it should be quite apparent to you, untangles immediately into the unknot, right? And we can take our trefoil knot as well and do all sorts of... Oh, sorry, that was pretty weak stuff. I should have made that a little clearer, but there we go. So this is just an extra twist, right? So here we're adding additional crossing. But it doesn't really change the nature of the knot. Adds an additional crossing. But it's easily undone. So that means there has to be some sort of basic difference between these crossings here and how they come together to make knots that can't be undone, and these additional crossings here, which come together to make knots that clearly can be undone. So in order to figure out what the difference between these sorts of knots are, we start to categorize this sort of thing, and we do that by calling them projections. And projections are actually a very useful mathematical concept as a whole, so it's a good thing for us to cover. Knot projections. Knot projections. Definition. So, different representations of the same knot are called its projections. Of the same knot are called its projections. Right? These are knots that have the same properties, mathematically speaking, but visually are very different. And consider this: projections of the figure 8 knot. This is kind of a cool knot that we will come back to a little later on, and looks like that. Perfect. So here's one particular projection of the figure 8 knot. I leave it to you to look at this next knot and to figure out that it is in fact the same thing. So here I go. I can do it. I believe in myself. I have the knot tying skills. If you look carefully and you rearrange this knot, you should be able to figure out that these two knots can actually be turned into the same sort of thing without doing anything crazy like cutting pieces of thread or something. Let me add one more that should be even easier to see in terms of its relationship to this knot over here. A very attractive knot, actually. Ta-da! Super cool. So these are 3 projections of the figure 8 knot. For other knots, so for simple knots, really, spotting projections is easy. But for much more complicated knots, at a certain point, you're not really sure whether a particular knot should untie or not, right? Is this a projection of the unknot? Up to you to figure out. Take a moment. It's right there. Should be nice and easy. In order to do it, all you would have to do is take all of these individual little pieces of string and flip them back and forth, right? So this piece can flip and unravel, but does that actually fix anything? Does that get us to an actual place where our knot turns back into the unknot? Looking at this, I think that this is the unknot. That's just a guess. Good luck, have fun, enjoy. Hope you're having a great day. Thank you very much for being here, and goodbye for now.